I'm going to start very basic with how you define variables in Matlab. And so first, this is the workspace in Matlab. So it works with lines of comments. So you see my mouse?
Yes.
Okay, good. So if I define something, for example, the variable a, which is a scalar, now it appears here. So it means that everything that I define here, now I define b, it appears here. So I input stuff here. I can see at any time what I've created, and it's listed here. And on the left, you see the folder where what Matlab can access. So here you have the path. It's useful to know that by default, the folder you are working in is in Documents Matlab. This is everything that Matlab can access. And if I want to access other objects or something else, I have to add the path. So something that is in my computer in another folder is not accessible to Matlab. So it will be useful at some point.
Quentin, I have a question.
Yes.
Because it's going to be the case at some point that, for example, this tab on the left where you have current folder, that people will close the tab and not be able to reopen it, which happens on things like Topspin as well. So how can we access that tab if it's closed?
Yes, that's a good question. I always make it.
I mean, I can write the question in the chat if they can't be answered, and then we can discuss them afterwards.
Yeah. I think somewhere there's a layout.
Yeah, it's in layout. You can open. You have show current folder, etc. It's everything is checked.
Yeah.
And you remove it.
And you can always put default. So actually, what I was going to show you first, I'm going to create a new script, because I'm not going to write what I show you here, because I prefer to have it in a script so that later on you can access it again. So this is I've just opened here to make a new script. I will save it because you can only run something that is saved. So I save it in Matlab and we'll call it tutorial 1. And now the list of comments that I write here will be applied in the, it will not appear here unless I specify it, but so here I will write a list of comments. And so that it's clearer, I will ask it to be, how do I do this? I did it the other day, I wanted to show you in fact, and now I don't succeed. There's a way. No. Doc, yeah. So this is more convenient because now what I will do here will be applied here, and you will see better what is going on. So it's always good to explain what you're doing. So when you put the % sign, you can write comments. So now I just give a name to explain what I'm doing, tutorial 1. And I'm going to create a section, define objects. And now I'm going to show you a list of different objects. So for example, I've just shown you how you can define a scalar. Very simply, you write a equals 1, and this creates a scalar a equals 1. If I run the code, I press F5, this runs the code. You see here, I've run tutorial 1, and it has created a scalar a equals 1. I can also run the code from here, and it goes through this code again. A very important feature that we will always use is if we put semicolon after a definition, it doesn't show. Yes?
Just something. You name it tutorial 1, but there is a space in the title, and when you wrote it, there is no space.
Oh yeah.
It's the way you save it.
Yes, here?
In the tab.
It doesn't need to be the same. Here, I'm just.
Yeah, okay.
It doesn't need to be the same. It will. This will be important where we'll define functions, but not for a script, which is just a list of lines of comment.
It's okay. Thank
you. Then, so this will be very important. If you forget about this, for example, I will show you later on with more detail, but if I write a big array of numbers like this, and I forget to put the semicolon, then I have this huge array, and it's a very convenient. So we always like to put the semicolon, and we remove them when it's very useful. Now, if you want to define vectors for row vector, for example, we use these brackets, for example, like this. So if I run the code, you see I define RV as a row vector. If I want a column vector, I have to write it like this. So in this case, it's row, and in this case, it's a column. Then for matrices, it's exactly the same. I will write row number 1, and then row number 2, and so on. Now you've seen this, so I commented it. Now if I run the code, you see M is like this. And for example, if I want to access the numbers in M, I can go here. If I double click on it, oops. It's useful for large arrays of numbers. So M, I can access it in a visual way like this. Now you can call objects.
So just Quentin, you write the matrices row by row. Row by row,
but in practice, okay, it's not very often that you will do this way. But now, yeah. In fact, there is an important example. If I want to add a row, I can do it like this.
Okay.
A way to add a row. If I want to add a column to O, I can also add a column to O. No, how can I do that? No, I cannot. It's not so easy to add a column. Let's try, in fact. So if I have O, no, it's not possible. Not like this, I think. Yeah. So you rarely do it this way because it's quite inconvenient. So usually I would use a loop. I will show you later how you define loops, but it's not a very convenient way to do it. Now, important point is how I can access this element that I have defined.
Can I just make a quick, maybe silly question first, which is if you write the matrix with letters instead of numbers, all the operations you can do on the matrix will be the same. If you make a matrix A, B, C, you'll still be able to use it in the same way.
You mean if I do something like this?
Yeah.
This doesn't work. So it's through an error.
Okay.
Because this is not Matlab is not symbolic. It only deals with numbers. What is possible is to write this. So this has created, these are char characters. So here I've created an array of characters, which is not the same as this syntax. In this case, it creates a table with this is a string and this is a character. So now if I write this, Matlab will be able to do it, but not if I have this. This throws me an error because this is now a matrix with A, B, and D on the first line, and then I have 4 elements on the second line. So Matlab is happy. So this is really inconvenient to work with letters in Matlab. So this doesn't work.
Okay, thanks.
So now if I want to access elements in the matrix or in the vector, it uses the way you would write normally in math. So for example, if I want to access the third element of this vector, I write it like this. So you see the third element was number 3, but this is what I've accessed. In a matrix, because there are there are rows and columns, if I have to specify the 2 of them. For example, this will give me the row number 1 and column number 3 of the matrix. I run the code. Oh, so sorry. So I'm going to erase this part because I want to work with numbers. So now in M, this is the first row. Sorry, first row is 1, 4, 7. Third column. Oh no, sorry. Again, this is the first row, and the third element is number 3. That's why I get number 3 here. Same thing with another example. Number 5. Once maybe if I open it here, it's clearer. Row number 2, column number 2. We can do this, but if I want to access a full column, for example, I want column 1, so I want all the rows of column 1. For all the rows, I write it like this. Same thing with columns. If I want the second column, for example, like this. There's another trick that is useful. If I want from the 2 to the last one, but I don't know how many rows I have, I can do it like this. So this goes from 1 to end, and I can also go from arbitrary number to end. Is it clear? We can also create sub matrices, for example, like this. If I run, let's recall what M was. So you see, this is M, and this calls row 2 to 3 and column 1 to 2. So row 2 to 3, line 1 to 2. So these 4 numbers that you see here. So these are just a few examples. Now I comment this. But we can also define more complicated objects that are called arrays. So for example, I can create for this I will need, before I introduce arrays, I will introduce a few useful functions. For example, if I have this one, bonds, this creates square matrix of size 3 by 3, with only ones in there. I can also create a vector with ones. Then I have to specify the number. The example will talk for themselves. So this gives me 3 rows and 1 column, or 1 column and 3 rows. And you see the examples here. So we have many examples like this, and we have the same, for example, and I will use it very often, the same with zeros. So this will do a 2x2 matrix with zeros in there. So this is, I will use it all the time. And there's another useful example, that creates identity matrices. So this is very useful when we do linear algebra calculations. But we can go to higher dimensions, and that's what I wanted to introduce. I'll just comment this. Higher dimensions arrays. So we have seen scalars, vectors, matrices, but we can also define arrays. So for example, now this is a 2x2x2 array. So the first, in this dimension, we have the first one, which is 2x2, and then in the second one, 2x2 again. I could have this, for example, also. Then I have 3 elements in this dimension, and all these elements are 2x2 matrices. And we can even, this works with all these matrices, all these functions. We can have 2x2x2x3, for example. And then it starts to be inconvenient to show them here. But if we don't need to read them like this, then it's very easy to access elements in there. For example, 1, 2, 3. This will give me the element of the first row, first column, and element 2 in this third dimension, and element 3 in this fourth dimension. Which is obviously a 1 because everything in G is ones. So now we have seen how to define the basic mathematical objects. There are other types of objects like cells and structures, but I think I'm going to keep them for a little bit later and focus on these more mathematical tools for now.
I just have a quick question.
Yeah.
For me, for what I recall from my mathematical classes, matrices can be from higher dimension.
Tensors.
You call array just the matrices that are from dimension higher than 2?
Yes. So I usually.
Or is it something different?
I usually say scalar, vectors, matrices, and arrays. But I mean, a scalar is a matrix, a 1x1 matrix. A vector is a
obviously
n by 1, and so array is a very general concept. So you can say that this is an array of 4 dimensions, and this is an array of 2 dimensions.
Okay, just to be clear on the vocabulary. So if you meant something else that I didn't understand.
Yeah.
Okay.
So I will mainly use Matlab's way to speak, which will be, as I said, scalar, vector, matrices, and use the word array for higher dimension objects. And a very useful tool is this. You have help and the name of a function, and then it gives you information on the function. And as I said, this is the way they define it. Matrix for a 2-dimension array, they call it a matrix. And yeah, so in this example, they use the word matrix, and I think array here. They usually use the word array when it's high dimensions. That's why I keep the same nomenclature as them. And by the way, a useful function is size. So if I ask size G, it gives me 2, 2, 3, 3, which corresponds to this. And for the other elements I've created earlier, for example, matrix M was defined here. M should be 3x3. Yeah, 3x3. So this gives me the number of rows and number of columns. So in fact, size M gives me a vector. So I can define a new vector. It will be size M. And now B is written here. has 2 elements. And by asking the dimensions using size, the dimensions of M, you create a vector that is B. So now if I want to access the number of rows of M, it's the element number 1, number of rows of M, while B2 will be the number of columns of M. So I will often, in a well-constructed code, you will always put a lot of comments to explain what you're doing. So sometimes I write a comment next to what I'm doing, so that we know what it is. So here, M had size 3 by 3. By asking size of M, I write it in B, and then I can call them. It will be useful later on. Now, new section, operations. By the way, I've discovered that recently working with Stuart, which is very useful, when you put this double comment, it separates in sections. And a very convenient thing is that you can run a section individually. So here, you can run a section, and you can also use the shortcut Control Enter. So if I do clear all is will erase everything that is here. If I click on, now I'm clicking on Control Enter, and it cleared everything. If I do the same here, it did all these comments, but not these ones. So if I run all the code, it does all this, but then it clears it. So one way to call a code is to do this section, and you will see it's very useful when we have long codes where we import data, we plot them, we fit them. It's nice to have sections. So operations. Let's say we want to create, to do operations between vectors, for example. So I'm going to create. I'm going to work with 1,000 points. So I will create a vector and do apply math on this vector, and my vector will have 1,000 points. So, and let's say we have time. So what is it? So before I do this, I'm going to show a little example. So here, this syntax creates a list of numbers that goes from 0 to 10. So this could be the time axis, for example, when you do a relaxation, you plot your relaxation data. So I've created this this vector. Now I want to plot a sine function of this. Can you do it like this? And so that I show you as I go how it works, I can plot this. Oops. I run it, and this gives me, so this is a vector with 11 elements from 0 to 10. Then when I write sine of this vector, it returns a new vector that has the same size. You see, 111, 111. And this function that we will use all the time, plot, shows you, gives you this, this plot. So I'm not going to give too much detail for now on how you plot. I will just use plot to show you the operations I do on the vectors. So there's this way to, when you take the sign of a vector, there's no ambiguity on what you mean, because there's no way you can play with vector using a sine function except by taking the sign of each element. So you can, it's straightforward to write it. It's much more difficult, you have to be more careful when you want to multiply elements. So for example, if I write a new function, a new vector, which is this also is easy. It multiplies all elements in T by 2. So if I plot it, you see it goes from 0 to 10, and when t is equal to 10, it gives the value 20. So it's a line, as we could expect. And in fact, from now on, I'm going to add this little comment here. It makes, instead of doing a line, it will plot as X. So it's clearer what data points we have. So just let me know if it's not clear. So, but I will tell you more about how you plot. For now, I just use them as a tool to show you what goes on. So now, more complicated, I'm going to show you how we get an error. So if I write t times t, then Matlab is not happy. Not happy because I'm asking it to multiply a vector with another vector, which is not defined in terms of math. You cannot multiply a vector, a row vector by another row vector. You can multiply a column vector by a row vector. So, and this returns a scalar. And this is something I don't really want to explain now. I will assume that we know a bit of linear algebra. But in linear algebra, when you multiply a row, sorry, of course, I forgot to explain you what this is. This is a transpose. So before I use it, I should show it like this. So T was a row vector. If I do this, I transpose T, and it becomes a column. And these elements I can multiply together. I'm mathematically allowed to do these two operations. I'm going to comment this because I don't want to have the plot every time appearing. So the answer to this one, because it's a row times a column, returns a scalar, while this one, which is a column times a row, gives a matrix. So this is basically linear algebra, and it's not very convenient to explain you how it works on this screen Matlab. But I'm not going to use that too much in the presentation. I just write here. So this is we said a column, a row vector. This row times column give a scalar, and column times row is the matrix. Oops. Yep. Now I comment this so that I choose not to display it later on. So it means that, for example, if I want to plot, I want to make a new plot, and I want to have this, like I did here, but I want to see the square. I have to add to help Matlab to understand what I'm doing. So this, as I said, will not work because this is the same as I did earlier with when I did this, I had an error earlier. This will not work, error. But what I can do to help Matlab, if I add this dot here, this, whenever there's an ambiguity on the operations that I'm doing, because I'm multiplying vectors or matrices and stuff like that, this will tell Matlab, you act element per element. So it takes all the elements in T and squares them, rather than using multiplication that as they are defined in linear algebra. So this will work. So I've run the code and I don't get a new mistake here. And now I can plot. This will work. Oh, and as earlier, I will show you this way. Yeah. So you see, I have, as expected, a parabola for 10. It gives 100, so it's what we expect.
I have a question.
Yeah.
Maybe you're going to come on to this, but I'll ask you before I forget. So here you create a list of time points, and that feeds into a function, and you can plot the result of the function against the time points. So this is the equivalent of list plot in Mathematica. So Mathematica also has plots where you can plot functions continuously.
Yeah.
Does Matlab have such a possibility?
Yes, you can. I've just discovered this, in fact. I'll just write this and then I will show you. Yes, you can. It's not the most usual thing to do in Matlab. But then you have to use fplot. So the syntax is like this. So if I want to show, I want the x variable to be time or t. Let's call it x to change. But I have to write at, and oops, and then I have to specify the boundaries. Just for your information, now I will use another way to call to run the code. If you select something like this, now if I press on F9, oh shit, it does just.
I think it's because it's x. Is it because it's x and then t squared?
You're right, and there's a second mistake, which is I should have the dot, I think. So if I do this, yeah, oh no, this works. So this is now a continuous plot. So if I zoom, as far as I zoom, it will always recalculate the points. Does it answer your question?
Yep, perfect, thanks.
But this is this can be useful from time to time, but it is not the most natural way to do things in Matlab, because most of the time Matlab is useful rather to deal with vectors and matrices and stuff like that. But in some cases, it can be really useful. I will come back to this later on, I think, in a more advanced part of the tutorial. So in a way, this does a sort of scalar product. It works for any pair of vectors of the same length. For example, if I have a row vector and a column vector, Matlab still understands what I'm doing. So I put the dot at the wrong place. Of course, this was wrong. Oh no, so this is not what I expected. I wanted to show you an example and it turns out to be wrong. So Matlab interprets this as the same thing as this. So I must tell you, I'm a bit confused with what is happening here. But this is a bit of a pathologic way to write the operation. So let's stick with this. So this will be very useful. And for example, when I will show you how to simulate a Laurentian curve, I will use dots. And sometimes you struggle to know where you have to put the dots when you do a series operation, and it can be a bit tricky, but you can get used to it. So for example, if I define a slightly more complex function where I have a scalar, and then I add the product of the square of t, now I have to put the dot because I want to square element by element. If I add another element that would be like, for example, let's do it like this, and divided by t, this will not work either. Because the division by a vector is also defined in linear algebra as a sort of inverse. So again, if I want to do a division element by element, I have to add this dot. Now, if I plot t and y for I'm gonna erase this for now because it creates this message. Let's put something bigger so that we see better what is going on. So we start at somewhere between 50 and 60. And so this is our function now. So I had to ask to add this point here because the division could be ambiguous. Now, if I add a sign, for example, for the sign, I don't need to put the point because there's only one way to interpret the sign. Same thing with an exponential. I don't need to add any points. Now that you understand how this works, let's go to let's make something a bit bigger. For example, if I want to simulate a Laurentian line width, getting an NMR experiment, I'm going to plot with 1,000 points. Let's say now I'm going to create a vector that is frequency in W. This function is quite useful. Linspace, it creates a vector. Oh. Let's say I'm want to go from 0 to 1,000 ppm, 100 ppm, and I want n points. So this will create a vector that goes from 0 to 100 with n points. So if I run this, now W has the number of points I wanted, 1,000, and it goes to 100. So I want to create a Laurentian function. Let's say it's centered at, so W0 is 50. So my scale goes from 0 to 100 ppm, and the center will be at 50. And let's say that the full width at half maximum is let's say 10 ppm, so that we have something a bit broad. Laurentian, I just give you the formula. Full width at half maximum is this. Full width at half maximum. So can you tell me if this will work? Can I calculate this like this? Or am I going to get an error message? Do you see any problem in this calculation?
Do you need dots here before division?
Yes, I need a dot here because in there I have a vector. So when I will divide, I want element by element. So I need to have a dot here. But there's another problem.
When you have W minus W0 square, it's the same problem. You have a vector that you same vector.
Yeah. Exactly. So this is a vector minus a scalar, which is interpreted as a subtraction of two vectors. And when I square it, I want to square element by element. So I need, so in this calculation, you need two dots. And now I will, let's call it S for signal. I plot the signal as a function of the frequency. And that's my nice Laurentian. You can verify that the full width at half maximum here, by the way, is as I wanted. Oops, around here. It should be something like 10. So because I've chosen the right writing the full root at half maximum this way is the right width. And if you want it to be normalized, quite useful to know, this will have an integral of 1 written like this. So it's kind of, it's more convenient when you do fits. And this is to my eyes, the clearest way to write the Laurentian function. Now something, I'm taking this example to show you how to do operations in Matlab. What we can do is to simulate relaxation measurements. So we have one Laurentian. Now I want to show you how to decay, to simulate the decay of a Laurentian. So I'm going to create a signal in 2 dimensions, which will be this signal multiplied by some timing. So let's say that T1 is 5 seconds rather. T I'm going to create as earlier. I say that I want a vector that goes from 0 to say 15 seconds, and I want to see 12 points, which would be a reasonable. I can create anything I want, but this is just to have something that is nice and visible. So this term here, I don't need to add any dots, because when I take the exponential of this vector, it will give me back a vector. But this multiplication will be wrong, because I'm multiplying S. S has dimension 1 by 1,000, and T, if I create T now, you see T has dimension 1 by 12. There's one operation that is legit, is if I take, to be able to multiply 2 vectors or 2 matrices, you want the number of columns of the first one to be equal to the number of rows of the second one. So if I take the transpose of this one, or let's say rather the transpose of S, now S like this has 1,000 rows and 1 column, and this has 1 row and 12 columns. So now the number of columns of this one is the number of rows of this one. So this operation is legal. I've run it and I get no error message. So it has created S2D, which has 1,000 by 12, which is what I wanted. And now this is this ugly table where each column corresponds to a spectrum. And if I want to plot it, I'm going to plot it as a surface, so it's another column. It's T times W times S2D. Might be wrong. Let's try. Right, it worked. So I just have a bit, slightly too many points, so it becomes very dark. I'm going to change something here. Instead of 1,000 points, I will plot 100, and the plot would be a bit nicer. Yeah. So is it clear what is going on here? Do you need any explanation on how I created this object? No, I guess it must be clear. So this shows you slightly more complicated operation than the first one we've seen. Vectors together to create a matrix, and each column of the matrix contains the a spectrum.
I have another question now. We're on this sort of topic. In Topspin, for example, you can create very nice stacked plots where the spectra are not only shifted vertically but also horizontally. Is there a way to nicely create such a thing in Matlab? If that's too complicated for now, we can look at it after.
You mean like this?
No, not quite, because you'd want to create. You want to shift each spectrum vertically, so that they're all separated by a certain amount, and then also shift them to the side so they're clear to see.
Oh yeah, there would be a way. So I haven't explained to you yet in detail how to use plot. For now, I was using an X value vector, a Y vector, and some options for the way I plot. There's a second way, is if you have a X value and a matrix. And in this case, it will create, it will take each column of this matrix and take them as and plot them as a line like this. So what I can do, this will be a bit more tricky to explain.
Yeah, if it's too tricky for the tutorial, we can look at it. We can look at it afterwards. That's not a problem.
Yeah, because in fact, if I just take this and I sum from 1 to how many I have, 12. 0, let's say 0 to 11. But let me just try it. So this did not work. I'm just gonna do a bit of trial and error and so this is from 0 to 11. This is 1 times 12. No, I want the opposite clearly. And I want 1 row and n columns. So now month is 12. Oh, okay. So I've separated them a little bit too much. So we can that's what you wanted? Sure.
Sorry, I was on mute. Yeah, that looks great. And I guess you can do a very similar thing for the X column, and that would shift them all to the side. And that would create the stack plot.
Exactly, yeah. This sort of thing is possible.
Yeah, it's very nice, thanks.
So I've been quite fast in the way I've constructed this. Because this takes a bit of practice to do such thing. Let's just, basically what I did here is to create this matrix. So it's columns. So when I sum it to my 2D matrix here, my 2D spectra, on the first column I add nothing. On the second column I add a little bit, and so on. And I've constructed this by taking a list of integers. It was too big a shift, so I've divided by some constant. And then basically what I did here, if I show you, I should have written it like this, in fact. I will construct a smaller example. This is what I wanted to do. Now it's a bit clearer written in this way. So if I want to write my example in a clearer way, I should write it like this. Yeah. And now we could do the same to shift them on the x-axis, and it would be basically the same principle. please don't interrupt again please don't hesitate to interrupt. So now, I just show rapidly, but I don't want to spend too much detail on this. Another operation, which is Conical Product. It will be useful when we will do simulation later on in a few weeks. So you can do a Conical Product between, for example, let's recall that this is the identity matrix in dimension 2. So if I call this, you see, this is the identity matrix. And I can take the Conical Product between this and say another matrix that I construct here. Which is a poly matrix. So if I show you let's write it in a clearer way. It would be IX. So now I've created the identity in size 2, the matrix of IX, and this creates a Conical Product of the two. So this is just to show you that there are other type of operations that are defined in Matlab and that can be useful. There's a large list of products that are defined. We have seen the scalar product, the matrix product, and now the Conical Product. I think I haven't given you any example of matrix multiplication. Of course, you can multiply matrices also using simple syntax like this, but I don't think we'll have many use of this in this tutorial. But yes, matrix multiplication works like this very simply. There were a few other functions that I wanted to show you. Maybe I can go back to the list of functions that I had shown. Where was it? Here. We can create random functions, list of random numbers. So this one, for example, no, this is not the place I wanted to write it here. So again, this creates random numbers. Because I put it 2, it's a 2x2 matrix. If I put 3, it would be 3x3. And 3 times 4, it would be 3, like this. Rand creates random numbers from 0 to 1 with equal distribution. There are other ones like, for example, norm rand, I've discovered recently. So I don't remember how it, here it tells me how it works. It will be centered around mu. There was a dispersity sigma. So if I want it to be around 0 with dispersity 0.1, for example, this will return a single number, I think. Yeah, single number. But if I want, I can then ask for, let's say, a 3x3. Yeah. So now, if you want to have a crash course on how to make up data, make false data, this is how it works. So I can add noise to the data I've created. So now to this matrix, I will add a normalized noise with a dispersity of 0. This will be far too much noise. Let's put it like this. And so that the matrix multiplication works, I'm going to tell it, use the size of this one. And I believe this should work. So there's maybe not, oh, I forgot to change the name. I was putting the wrong one. I'm going to move this one up. Yeah, so maybe there's a bit too much noise here. I decrease it here. Yeah. This is a way to create your false data. And of course, for skirts, we can also do it like this. Now I'm plotting them line by line. I was obviously kidding and saying that you can make a data, but it's just interesting to know being able to create this false data. To me, is quite instructive on the way noise behave. Do you have any question on these random functions? If not, I continue with a very important concept, the statements. Very often we want to verify if conditions are verified. So let's say, for example, that I have A equals 1. I want to do a certain operation only in case A has a certain value. But if I say A equals 2, and the bit of code that is in here will, for now there's no code, but the bit of code that will be there will only be evaluated if this conditions is right. And you have to use this double equal. And this will display something here, so condition fulfilled. So now if I run this code, nothing happens because this is A equals 1, so when it checks if A equals 2, it's wrong. Now if I do this, it does write it here. So for example, we could do it like this, and then there's another statement, else this. So if I run the code, it says condition fulfilled. Now if I say if A equals 2, you write conditions fulfilled, and else. So if this is not true, you write condition not fulfilled. We can also add else if, and then another statement. This is probably the first case, but it will evaluate first. Okay, is A equals to 2? No, so I don't do this bit of code. Is A equal to 3? No, so I don't do this bit of code. Else, I do this bit of code. No condition fulfilled. Now, if I write 3, you see second condition fulfilled. So this will be very, very useful in many situations in Matlab. Then we can do two statements. If A equals 3 and you have to write it like this, and B is different from 3. So this syntax is wrong, sorry. Yeah. So this syntax means is not equal to. You can even add another condition, and C is larger than 5, for example. Oops. Oh shit. Now if I run the code, I'm just going to add a space here so that we see. So by doing this, I just add a space. Yeah, so we see a bit better. So it did show this one, but not this one because A is equal to 3, but B is equal to 4. Now if I change the value of B, all these 3 conditions are fulfilled. Another comment I can make is that it only, if this is fulfilled, it will do this, but then it goes to the end of the loop. If you have this one and this one that I completed, so let's say if I ask if A is larger than 0, as if A is equal to 3, and condition 1, condition 2, well, here I forgot the double equal. Then in this case, it will only do the condition 1, because once the condition is fulfilled, it escapes the loop. It doesn't consider a second condition. So this is for the if statement. There's a very important now is the for statements. So if I start with an example and then explain it. Let me separate it, if statements. For loop. So what, again, so what does this do? This loops a condition. So the first time I is equal to 1, and then it will increase it. So the second time I is equal to 2, and last time I is equal to 3. And each time it goes to the code, it displays I. This is, so we can, for example, with a more complicated example, if we have, let's say, T, oops. I write the example and I will explain it. So what I'm doing here, I create a vector T with n elements, and it goes from 0 to 1. And then in this loop, I will take value from 1 to n, step by step, and it will calculate for this function g in the I element. It will put the I element of t multiplied by 10 and taking the sign. So I run this code, and then I will plot the results. So this has calculated the elements of G one by one using this loop. So here, this is just to give you an example, because there are two reasons why this is an unclever way to make a calculation. First, I'm using G here, and there's a message. The variable G appears to change size on every loop iteration within a script. Consider pre-allocating for speed. So pre-allocating would be to give G the size it will have in the end. And I know in this case that G will have this size in the end. It would be a row vector with n elements in there. So if I just give it some, when I do this, G now is just a list of zeros, but it means that the computer has already assigned some space to store the value of G. Because here, if you don't do this, so if I comment this line, it's not active. I have this message, this warning telling me that it's not very clever. When it's n here is only 100, so it's not playing a big role. If it's an array with 1,000 times 1,000 times 1,000 elements, or a billion elements, allocating the space at every iteration will take a hell of time, and so you prefer to. In my codes, I always, whenever I know the size of a vector, I will always give it, save it like this, and then rewrite the elements one by one. The second reason why it's not so clever, and I will show you an example here. So I copy this. Now, let's say that let's take our example that we had here. I'm copying all this with a large number of points. So 1,000 points in this dimension, and the second one, m equals 1,000 as well. So now this vector will have 1,000 points. So I can put it. Yeah. Same thing with same thing here. Okay. So I have my decay. Both of them with 1,000 points. I can create, using a loop, rather than this, I'm gonna create S2D, so this signal in 2D, I'm gonna create it as zeros of m times n. So the number of columns is the number of time points, and the number of rows is the number of points in the spectrum. So it means that I have each spectrum as a column. Let's increase it to even more like this. So there's no reason why I wouldn't be able to make my calculations like this. It's in a loop, and now I'm gonna calculate this element. Oops. Using, so this was my, let's make it easy like this. So doing this calculation, I don't need to put any dot here because Si is a scalar, Dj is a scalar. So when I multiply them, it's just the multiplication of two scalars. There's nothing complicated about this, no ambiguity. I just have to make sure I've used the right numbers. So n here is, I goes from 1 to n, and n is 1,000. And S was defined as the right, yeah. So now I can do the same plot as I did earlier. I'm gonna call it back this surface plot. It's without noise for this one. So now it's computing. The result is very slow. Got that many points. I just have to wait. Yeah. So of course now it's all black because there are so many points that we don't see the colors anymore. And when I try to turn the surface, it's very slow. What I wanted to show you in doing this is I can use this command tick and tock. It's very useful. So if I type tick and then tock, it tells me the time that elapsed in between the two. So here I will show you how long it takes to do this calculation. It's not so long, it's 0.1 second. But doing with the appropriate way to do it, which was this way, we'll see that the tick-tock is just no comparison. And I comment this because this is very slow. So you see, this way to do the operation took 20 milliseconds. This way to do the operation took 100 milliseconds. And if we increase the numbers even more, it will be even slow. The difference will be more stringent, I think. Yeah, there's still a factor 10, more or less. And if you increase, so now it's only 2 dimensions, but if you go to high dimensions, the difference will be more and more pronounced. So this is the really appropriate way to do calculations in Matlab. When you can avoid to use for loops, you do it, because this is Matlab is so well optimized to do calculations this way that when you do it like this, it's very slow. Of course, you will use for loops for special cases, but not for, in principle, you don't do it for calculations like this. There's another useful statement, the do statement, do loop, sorry. So if I say that n equals 3, for example, I call it the, no, let's call it the while. This is, in MATLAB, this is more the way it works. So it will be clear in a minute what I'm doing. So this will run the code that is written here as long as the value of n is below 10. And a perfect example of this is this. If I run this bit of code, first time it entered the loop, n was smaller than 10, so it entered. And it did n equals n plus 1, so it incremented to n. Then I display n, so I have 4. And it will loop it until n reaches the value 10, and then this is no longer true. You can also write it, maybe it's clearer, the example is clearer if I do it like this. It's stop at 9. You can also do it with an equal here, and the result is obvious. It's when it's smaller or equal. So all these loops and statements and all this will be building blocks for constructing NMR data and stuff like that. Now I wanted to show you some elements on how to make plots. I think, but I'm gonna show you first how to import NMR data, because this is really, it would be more interesting to create plots on the NMR data. So to importing NMR data. I think this is really where it gets interesting in the tutorial. To do this, I personally use a function that I recommend to use. It's very, very convenient. It's called rbnmr. I can share it with you if you're interested, and it's just available on internet. It's someone who created it and made it available to everyone. So this function is very easy to use. So I'm going to store let's call it this way, NMR data. You just have to specify the path that you want to import. So I have an example here. This is my NMR data. Experiment 150. It's a pseudo 2D experiment. So it's a DNP experiment, and I need to find the folder where it is stored and specify the MATLAB. So it's in my Brooker data. It's this one. I take the path and I type it here. And you see, this tells you what it is doing. So these numbers here correspond to the different elements, 1, 2, 3, 4, 5, 6, 7, 8. I don't know why it didn't import the 9th one. Anyway, so now this element is here. Let's open it and see what we get. This corresponds to the prox. So when I double click, I haven't shown you yet what a structure is, but a structure, so let me just show you as an example. I can create this. So for example, this has just created A as an empty structure. This is maybe more clear, appear like this. So here I'm just showing an example to you where A contains many different things that have nothing in common. So the first element of A is a scalar, it's 1. The second element is a character, and the third element is a matrix. If I do this, now I can access in the cells these different elements. They don't need to relate to each other. I can even create larger dimensions. And be careful, you have to use curly brackets when you use these elements. So, yeah. Now, because I have added a dimension, oops, it didn't work. I think I didn't run the code. Apparently, this doesn't work like this. I should do it like this. Oh, sorry, I've overwritten it right now. Yeah. So now I have the first line I have defined, the second line, and I have defined nothing for these two bits. So now I can call if I want an element like this. That example. Yeah. So I had written E here, so I can reuse the element. It's very convenient, not for calculation because you cannot multiply these elements. It's not defined on them, but it's useful when you have typically like NMR data, as we will see, to store large arrays of elements. And another interesting thing we can do is to define if I do this now F, let's do other examples. F dot A. When I use this dot, F becomes a structure, and I can access different elements in F. So F of H becomes. Let's do a larger example. F contains a list of variables now. So and rbnmr uses both these concepts. It's useful to know how they work. So now that we know how these things work, we can understand how rbnmr has imported the data. I click on them. I have a list of structures that correspond to procs of topspin, and now I have in this list. I have, for example, the title of the experiment. I have info on the experiment. I don't know exactly which one. The file path, stuff like that. 2RR means 2D, I believe, and in particular, important the data, the acquisition parameters. For example, the number of scan is somewhere here. NS number scan. The gain is RG is here. It's useful to know. So you see, you have like really everything that that topspin does and saves is in here. And of course, more importantly, the x-axis is the frequency axis, and y-axis is the actual signal. Oh, sorry, but usually we use more data because data has each line corresponds to a spectrum. Because this is a 2D experiment, so data is a 2D matrix. It's a matrix. So let's see how we can play with this and, for example, plot a spectrum. I'm first going to show you, because I don't like the fact that we have these 7 elements here, and I always use only the first one when I work. I don't care about the rest. All these ones, I don't use them. So what I do is I always erase the number 2 to 7 in a very simple way. I write NMR data is equal to NMR data, and only the first one. So now that I run this one, it imports everything, and now NMR data only contains this. They are no longer, so you see it's a 1-by-1 structure. It's no longer these lists that we had earlier. If I want to make a plot of my NMR data, how do I access them now? I have x-axis, and I told you I have data. If I do this, I think it won't work. Oh yes, it does. So it has superimposed because Matlab is clever. It found the dimension of this. This is now a matrix with on one dimension is the same as this one. So Matlab knows if it has to take this or the transpose. And now it has superimposed all the spectra. It's extremely slow now because if you calculate how many elements you have in size, just to show you how many elements there are on this graph. This is the number of points you have on this graph. So of course, it's a bit difficult to do visualization on this, and rarely we will use it like this. So let's see how we can make this a little bit more convenient. Instead of using these big names, I'm gonna create my axis for frequency will be this one. So now it's called W. And my signal in 2D will be NMR data here. And my convention is that I always use a bigger transpose, because the guy who has coded rbnmr puts spectra on lines, on rows. While for me, the natural way to store data is to store them as columns. So I take the transpose, and I think Matlab will still be able to plot it. Yeah, even though I've transposed it, Matlab is still able to do it. So this displays all the elements. But now if I want to display, for example, only the first graph, this is, if you recall how I explained you could access elements in a matrix. Now I take all the rows and I take the first column, which corresponds to the first the first spectrum. Just so I do this because now I can run this code simply by pressing on Control Enter, I guess. So now I only have one element on this plot. You see, for example, this nice hyperpolarized signal. Now let's see a few examples of the things we can do. So region selection and integration. Usually, what I personally do, I create a figure. So by the way, you may have noted that every time you have two plots in, so for example, if I do this, you could expect that it creates two plots. but because I have two plots in one after the other, it erases the first one. So if you don't want to have this, you have to create you type figure, and this will create two separate figures. You have figure 1 and figure 2. And now, if I run this piece of code again, it will erase figure 2 unless I write figure again, and then I've created a third one. So this is the sort of thing that you will discover by trial and error. It's not too difficult. But you can split your figure, and this is very convenient by doing subplots. I want a subplot with 1 row, 3 columns, and now I want to plot element 1. You will see why I'm doing this in a second. So just so that you are not lost in what I'm doing. This code opens a new figure, and now I have a grid of 1 row and 3 columns, and in the first element it will do this plot, in the second element this plot, and so on. Oh, and I did a mistake. Yeah, so I have 3 plots now. Why do I want to do this? Is because usually what I do is I first write the first spectrum like this, and I did not put the x-axis. So what does it do? It plots, but here the number, the x-axis is the number of the points. So S2D has this number of points. So each spectrum has 32,000 points. So the largest x value here is 32,000. So this, yeah, you can zoom with these elements here. The reason why I want to do this is I want to select a region of my spectrum. So for example, I want to select a region to integrate it, let's say from 3,100 to 3,500. If I do this, I will have an error message because these two vectors do not have the same size. So here I've taken from point 3,100 to 3,500, but I have to do the same thing on the frequency axis. So now this could become what I'm gonna sum later on to do the integral. And from time to time, what I also do is I define a region for the noise if I want to do calculation of the of error. So for example, if I know that if I take from 13,000 to 15,000, 13,000 to 15,000. Now I have defined a region for the signal and a region for the noise. So I can use these two regions for signal to noise ratio calculation and integral and all this. A few other interesting things that you can do is to add a title. The easiest syntax is like this. Whole spectrum. I'm gonna put a title for each of these plots. This is signal. This is noise, and I can add labels. So X label is a syntax. You can find it all on the internet, but I show it rapidly. So this will be a frequency in BPM. I can add this for all of them. Same thing with the y-axis, which will be the relative intensity in arbitrary units. if I run the code, I've added the ranges, these labels, and what else can we do? There are many to play with this. With graphs, there are loads of things you can do, and it's useful to refer to help plots, and then you can read a little part of what you can do, but there's really a lot. And if you ask on Google, there's really a lot of information. It's quite easy to find. People give you advices on this. So now I've defined. This is something I do usually in the start of my codes. I can create SB will be my signal boundary, so I like to do it like this most of the time. And I do the same with noise boundaries, so that I can call them later on. So now this became SB1, SB2. The reason why I personally do things this way is because it is convenient when you want to go back to your data and know, oh, but how did I do the integration on this plot, and what did I do with it? Then if you save things like this, first you can create a new plot just by copying this and just changing these values. And second, you know exactly how we have done all the calculation. So obviously the result is the same. And if you remember, I have this number here, the 1, which means that I'm playing with the first signal of the decay of this high-pressure experiment. But now what I can do that is interesting is to do the sum, so the integral of the signal. So so I want to calculate the integral. For this, I will use this function, which is simply the sum. So I will sum for each spectra. So to do it on each spectra, I use this one here. I take this part of the spectrum from this, the boundary 1 to the boundary 2. And I want to sum, and here I have to specify that I want to sum over dimension 2. Just to give you a little, if I have, what can I, just to give you a simple example. So I've created this matrix D, and if I take sum of D, it sums the columns. But I can specify if I want to sum all the dimensions, for example. It will give me the sum in this dimension, but also the sum in the other one, so it becomes only one number. And I can also choose which dimension I want to sum. So in this case, in fact, if I don't even write, this is one of the reasons why earlier I told you that I always take the transpose. It makes more sense because when you have your data as columns and not as rows, when you do the sum, it's more natural to Matlab to sum in this way. So now I can make a figure with this. I tell it to you, but it's not. So if I want to create the time axis for this decay, I can do it like this. So it goes from 0. Let's pretend we know how many. It's 256. I will show you earlier how to automate it, but for now, let's do it like this. So this creates a time axis that goes from, so it's 5 here. It's 5 seconds between each point. But this I know from because I did the experiment. And now I can plot T and I. I did the syntax mistakes. It's lin space. Not a mistake, apparently.
Is it, Quentin, is it that you need the 1 in I at the end?
So apparently I is now 256, which is, you say this one?
Yeah.
It is still wrong. But 256 is right. So this one should not change the results. So we have I is 256 and T is 255. Oh no, this is the wrong part. It goes from 0 to 5 times 255, but I want 256 points. Yeah. And here you see your hyperpolarized decay. Then what we can do is normalize it. So I divide it by its maximum, so it's the maximum 1. And to make the figure nicer, we can do things like this, add a grid. So the grid is these lines here, make it more beautiful. What else can we do? We can set limits, because Matlab sometimes shows limits that I don't really like. So what you can do is for the x, you go from the minimum of t to the maximum of t. We can set a limit for y that is a bit nicer too. I usually go for this sort of data. This is what I choose. That's well centered. Yeah. Of course, I can add labels. The x label will be time in seconds. And the y label will be relative signal integral in arbitrary units. So now I have my plot like this. What else would I want to show? I can also, so here I've written this by hand, but it's more convenient to my eyes to do it like this. So I can say, okay, I want to use the size of S2D, and size is a vector, so I have to choose S2D. It's the second dimension, so the number of columns corresponds to the number of spectra. So instead of writing it by hand, I can do it like this. Same thing here. And this I want to use D1, and I don't. So I'm going to show this to you in NMR data. In acquisition parameters, I have all the Ds. There's something very stupid in the way it's done, because on topspin, the delay starts with D0. It's shifted here, so D0 becomes D1, and D1 becomes D2. So unfortunately, if I want to access D1, I have to write D2. And so maybe I should have explained that this delay D1 in this experiment is the recycled delay. So we have injected the hyperpolarized solution, and after each delay D1, we have taken a spectrum. So to access this, I go in NMR data, ACQUS. I just check that it is right. NMR data, ACQUS, and D. And I want the second element of this vector, and this is D1. So now I can replace this by D1. So now in this fully automated way, I generate this, and if I do a new experiment, I can just repeat my code. And I don't have to type by hand what was the value of D1, what is the size here, and all this. There's another little trick. For example, if I had, it will not be very impressive in this case, but it is still useful to know. Here, if I transform my spectrum with more points, I have only zeros here because I have too many points. So let's see what happens when I import this data. Because for me, it's often the case that my data are done this way. So I import them again. Now I can show you the same thing here. So now when I do this, of course here, I have only zeros at some point. So I came up with a little strategy to remove automatically the zeros. I'll show you how to do it. So I take n, I will take size of, of this one, and number 2 is the number of spectra. And now I'm gonna use this while loop while sum of this guy I write the code and then I explain it to you because it's tricky. So what does this trick do? This is spectrum number n. All the points of spectrum number n. So here I've placed the parentheses as a wrong spot. So I sum them all. So this is the integral of the full spectrum number n. And if this is 0, n will be now n minus 1. And it loops this. And at the point where there will be any point in the spectrum, the integral will no longer be 0 and it will not do the condition. So what I then do is that I tell it now you replace this by all the lines and column 1 to n. So it has what it does, it replaces right like this. I have removed, let me show you again. When I import, and then I create S2D. S2D has 512 spectra. Now, when I do this code, after it, it has 256 because it has checked spectra by spectra starting from the end if there was something in there. And so in the end, it just chops all the spectra that had nothing in there. So in this case, of course, it was not useful. I just artificially added some zeros, but very often when you do relaxation measurements, you maybe have transformed with 16 points, but you have acquired only 12. So to automatically remove the empty points, this is a convenient way. This is plot return to equilibrium. Relaxation data. So this is all I wanted to show for today.